Imagine holding something so impossibly dense that a single sugar cube of it would weigh more than every car on Earth combined. Now imagine that object is the leftover heart of a star, compressed to a size smaller than a city, yet still packing more mass than our sun. These aren't creatures from science fiction, they are neutron stars, some of the most extreme and fascinating objects in our universe. They represent the ultimate triumph of gravity, squeezing matter to its absolute breaking point. How does something so unbelievably dense come into existence? What bizarre forces are at play inside them? And what happens when a star dies in such a spectacular fashion? Today, we're going on a journey to the stellar graveyard to explore the incredible physics and cosmic drama behind neutron stars. We'll uncover how these stellar remnants form, why they pack so much punch into such a tiny package, and meet their famous cousins, the pulsars, cosmic lighthouses that sweep beams of energy across the galaxy. Get ready to have your mind bent by the sheer weirdness of neutron stars. At their core, a neutron star is the collapsed heart of a massive star, one that was likely 8 to 20 times more massive than our own sun during its vibrant lifetime. Think of it like this: when a very heavy star runs out of fuel, it can no longer support itself against its own immense gravitational pull. The outer layers blast away in a spectacular supernova explosion, but the star's core, its very center, collapses inward with unimaginable force. And it just keeps collapsing, shrinking, getting smaller and smaller, until it reaches a state of density that's almost beyond human comprehension. It's not just dense, it's a completely new state of matter, unlike anything we encounter on Earth. This tiny, super-heavy remnant is what we call a neutron star. It's a stellar corpse, yes, but one that still holds incredible power and some of the most mind-bending physics in the cosmos. To truly appreciate a neutron star, we need to understand its dramatic birth. For most of its life, a massive star fuses lighter elements into heavier ones in its core, releasing energy that pushes outward, balancing the inward pull of gravity. But once the core tries to fuse iron, the process stops producing energy. Suddenly, there's no outward push. Gravity, unopposed, takes over with a vengeance. The core begins to implode, falling inward at a quarter of the speed of light. This isn't just a gentle collapse, it's catastrophic. The atoms, no longer able to resist the crushing pressure, are literally torn apart. Electrons are forced into their protons, creating, you guessed it, neutrons. Imagine a crowded room where every person is suddenly squashed so tightly against another that they merge into a single, new entity. This immense inward crush, transforming almost everything into neutrons, is precisely what gives the neutron star its name and its incredible density. The outer layers of the star, unable to withstand this sudden collapse and rebound, are then violently ejected in that dazzling supernova explosion, leaving behind only the ultra-dense neutron core. So just how dense are these things? Well, imagine taking all the matter from our sun, a star so large it could hold 1,000,000 Earths, and compressing it down into a sphere roughly the size of a city, maybe 10 to 20 kilometers across, like Manhattan or London. That's a neutron star. Its density is such that a single teaspoon of neutron star material would weigh billions of tons. To put that in perspective, if you could somehow bring a teaspoon of neutron star material to Earth, it would weigh more than all of humanity combined. This extreme density is possible because the star is no longer made of individual atoms with vast amounts of empty space between their nuclei and electrons. Instead, it's a solid, gargantuan atomic nucleus packed almost entirely with neutrons. These neutrons are pressed together so tightly that they generate their own outward pressure, called neutron degeneracy pressure, which is finally strong enough to halt gravity's collapse. It's a standoff between the most fundamental forces of the universe, holding together something that defies our everyday understanding of matter. Now, many neutron stars are also known as pulsars. When the massive star collapsed, its core started spinning faster and faster, much like an ice skater spins faster when she pulls her arms inward. This rapid rotation, combined with an incredibly powerful magnetic field, creates something truly extraordinary. As the neutron star spins, its magnetic poles emit intense beams of radiation, usually radio waves, but sometimes X-rays or gamma rays. Because the magnetic poles aren't necessarily aligned with the star's rotational axis, these beams sweep around like the light from a cosmic lighthouse. When one of these beams happens to point towards Earth, we observe a quick, regular pulse of radiation. And regular is an understatement. Some pulsars are more precise than the best atomic clocks on Earth, spinning thousands of times per second with unbelievable stability. These celestial lighthouses provide astronomers with incredible tools for studying everything from cosmic distances to the very fabric of spacetime itself. Life inside a neutron star is as alien as it gets. The gravity on its surface is billions of times stronger than Earth's. If you were to drop a teacup onto a neutron star, it would hit the surface with the force of a nuclear bomb. The internal structure is theorized to be layered, almost like a planet. Beneath a thin, incredibly dense crust of iron, there might be a liquid ocean of neutrons, mixed with a few stray protons and electrons. Deeper still, at the very core, the pressure is so immense that scientists aren't entirely sure what happens. Some theories suggest exotic states of matter, like quark-gluon plasma, where even neutrons themselves might break down into their fundamental components. This extreme environment makes neutron stars natural laboratories for studying physics at densities and pressures we can never hope to recreate on Earth, pushing the boundaries of our understanding of matter and the universe's fundamental laws. They are truly cosmic marvels, silently showcasing the universe's most dramatic physics. From their violent birth in a supernova to their existence as some of the densest objects imaginable, neutron stars are a testament to the extreme power of gravity. They are not just dead stars. They are active, exotic laboratories of physics, spinning faster than anything else in the cosmos, emitting precise beams of light, and holding the secrets of matter at its most compressed. They remind us that the universe is full of wonders far stranger and more magnificent than anything we can invent. The next time you look up at the night sky, remember these invisible giants, silently illustrating the breathtaking power and complexity of the cosmos. If you enjoyed this journey to the heart of a neutron star, consider subscribing to explore more of the universe's mysteries with us.